Hello, this is our second video on circular motion. In this case, we're going to be solving an exercise. Here is Dr. Rafael Quintero Arcaya speaking. Okay, we are taking this frame from the movie Mother of the Orient Express, who graciously placed it on the web, and we are taking it to as an introduction, as a pictorial introduction of the topic. The first video was on circular motion, and there what we did was lay out the basics of all of this topic. Now, in this video, we shall describe the physics of a train taking a curve, draw its free body diagram, apply Newton's second law, find the centripetal force for two conditions, one radius and then a different one. And then you are going to be computing the ratio of those two forces. As you are seeing on this photo, taken graciously thanks to the website Pexels, and the artists are putting in their work in there. We have this train that is sloping down a hill, as you can see. Our case is going to be, and it's curving, and it's sloping down a hill. Our case, we're going to take a train that is just curving, but it's flat. Okay, the road is flat. We're going to do that because it is a simpler case. Still, we're going to get the gist of the physics behind all this process. For that, we're using this setup. It is a historical site. This is the horseshoe curve. Okay, and this picture was taken in fall, as you can see by the foliage, how colorful it is. The horseshoe curve in Blair County, Pennsylvania, outside of Altona, USA. That's the one we're using. And even though this is a very beautiful picture, we're using the following. Another point, and it's the fact that the diameter is 400 meters. That's about the length of four soccer fields. Okay, that's about the length of 4 soccer fields. Now, this is an aerial photo taken by the United States Geological Survey. This is a better photo for our purposes, and it was taken in winter, as you can tell. Now, how good is a circular approximation? Well, we see there, it's not a bad one, okay? Yes, there are some places that it isn't that great, but still, it's going to be useful looking at it as a circle. And there is the diameter, and there is the radius. Whenever we're trying to solve a situation that is real, very often we're going to need to make simplifications. In our case, there is one here, and it's the fact that the diameter is quoted at 400 meters. As you know, this means only one significant figure, and we're going to assume that we know it with 2. So that's 4.0 times 10 to the square power to the second power meter. The train travels at a constant speed of 8 kilometers per hour along the curve. That's a slow speed. I'm sure that the actual speed must be either maybe twice or 3 times as big, but we are in the bulk. The train does not lean, so the tilting angle is 0. By that we mean that the train it's curving just very flat, okay, along the path. It's not tilting. And that means that the train is very stiff as it goes along the curve. That simplifies the analysis. Besides, we say that the average mass of the passenger wagon is 60 tons. That's 6.0 times 10 to the 4th power kilograms. As we saw in the first video, whenever we have an object that is going along a circular path, the force all the time points towards the center. So, and the acceleration turns out to be just the square of the speed divided by the radius. And the centripetal force, because it's going around a curve, we call it centripetal, is the mass multiplied by that acceleration. So we're using that expression. We strongly recommend that you organize your work this way. On one quadrant, you're going to place sketches. On another one, data and conversions, equations and algebra, and calculations and results. Okay? This is a very good way that you can organize your work. You may do your work somewhere else, but then you bring your final results in here so you can review them readily, and your reader can note in a shot what's happening everywhere. Now, we saw that the diameter was then 200 meters, 400 meters. Okay, so the radius is 2.0 times 10 to the second power, and the mass, we already stated, was 6.0 times 10 to the fourth kilograms. The speed, even though this is a very convenient unit in terms of when you talk to someone, it's not a very convenient unit in physics because we need SI units. And we need to convert these kilometers into meters. And the hours, of course, we need to convert them into seconds. And a good way of doing that is by applying the unitary method. And in this case, essentially, the moral is that you have kilometers here, you need to cancel them. And a good way of canceling it is by putting kilometers at the bottom in a fraction. If you put it in the denominator, on top you say, okay, 1 kilometer is 1,000 meters. So meters are going to stay on top. For the other one, we need to take care of the hour here. So we need, this is in the denominator, so we put it in the numerator here in this factor, 1 hour, and 1 hour stands for 3,600 seconds. Out of that, you end up with a calculation of 8,000 meters divided by 3,600 seconds, and that yields 2.2 meters per second. Now, look, we need to be cautious and keep track of the number of significant figures. There are 2 here, so we should have 2 there, okay? So that's why we're gonna be working with 2.2 meters per second from now on. In terms of sketches, we have this woo-woo train going around. This is the circle, this is the radius, and it's going along the path. And what is really beautiful about all this is, look, when we have the rails and the wagon over here, look, we have the vertical forces. What are those? Those vertical forces are going to be the weight, because we're in some planet, maybe on Earth, and the normal force, because there must be a force by the ground so that the train doesn't fall. Okay? So, and we call that the normal force. Those 2 are vertically. Horizontally, on the horizontal plane of as the train travels along the curve, we have a net force. And look how interesting this is. When the pilot turns the train, okay, it's pushing on the rails. But the rails push back on the wagon, and that's what makes the wagon turn around. That's what makes the train turn around, okay? So that's the origin of the centripetal force, the reaction of the rail towards the pushing of the train. And that's what makes the train turn around. We call that centripetal force, and we have it there. And now we're going to do some equations and calculations. We already said there is no motion vertically. So the 2 forces that are vertically, those are the normal and the weight, they need to cancel out exactly. The way to do that is that the normal force becomes exactly the negative of the weight. And we know that the weight is mass times acceleration of gravity. And that's our first equation here. Now, we see on this photo that we have this long train. The train is pushing on the rails, and the rails are pushing back on the train, and that's what makes the train go around. And we have that the net force is the centripetal force. It's going to be the mass times the square of the speed divided by the radius. Okay? And that's our second equation. So we're ready for doing some calculations. We take the mass multiplied by acceleration of gravity, 9.80, and we obtain the normal force. The normal force should be 5.9 times 10 to the 5th power newtons. Remember that the unit for force is newtons. Now, look, again, we have 2 significant figures here, 3, so the result should end up with 2, because what prevails is the least number of significant figures. That's the one that prevails. Also, another, we have to be cautious not to confuse normal force, which is a vector, with capital N being newtons. Okay. For the centripetal force, we're going to just put together all the values that we already have. The mass, 6.0 times 10 to the fourth Newton. The square of the speed, 2.2, and then divided by the radius, 2.0 times 10 to the second power meter. When we square here, you have to be careful. Even though you may end up with many numbers, the calculator may give you many numbers, you only have to, the result has to be expressed only with two significant figures, the square. If you do that, you end up with 1,440 kilograms meters per square second. We recognize this is newtons, the unit for force. So we're going to end up with 1.4 times 10 to the third power Newton. Again, we're respecting the fact we're applying the rules of significant figures. We have two significant figures here, two there, so we end up with two significant figures. This is the way your work should look like. And this is essentially, this is going to be a very effective way of you displaying your work. And also, it's going to be very useful for you to review. Now, the second situation, look at this. We have this artist, Mr. Sharon, that provided this, this beautiful piece of work. And here we have this very smooth and some very tight curve. We already saw one tight curve. We're going to go into a smooth one. This could have been made from plaster, or maybe painting, or maybe even ice cream. Okay? So this is the original work. I just triple it and play with it on this part. Now, this is what you're going to do. We shall examine some features of, as the train goes onto a softer, smoother curve. And to do that, we took the second curve, the one that comes just out of the first one that makes the shoe horse curve. If you do some scaling of the radius here to this one, you find that that radius comes out to be about 1,000 meters, 1 kilometer. That's a very convenient number to use. We have another artist providing with this beautiful photo. I just double it, okay? And also it has to do with the train station over here. And what you're going to be doing is the following. You have the radius. So what you're going to be computing a new force. And this new force, you're going to hold the condition that the speed is the same. That's what you're going to be doing. And then on your own, you're going to be computing the force. You're going to find out whether the force decrease or increase relative to the initial one. So you're going to find that factor. That's, you are going to be on your own doing that one. However, I give you the results. The final force, the second force should be 2.9 times 10 to the second power Newton. The radius, the ratio of the initial and the final force, depending on how you do it, it's going to be 4.8, sorry, or 5.0. We'll discuss this difference later in our third video on this topic. But those are the values that you should get, depending on the way you do it. Now, in this video, we have described the physics of a train taking a curve. Its free body diagram, applied Newton's second law, found the centripetal force for two conditions, the initial radius and the final radius, a bigger one. And you computed the ratio of those two forces. Okay? This is just to bring up the next topic. And is, look, this worker is preparing a steel frame, okay? And it can be a very cagey object. Why? Because they are going to pour concrete into it to make reinforced concrete. And that's the topic of our third video, reinforcement. We're going to be reinforcing on this concept. I hope that this video has been useful to you. I hope to see you on the next one. And this was Dr. Rafael Quintero Arcaya talking to you. Thank you.